Okay, a few just conceptual things here. Shouldn't take that long, and then I have some practice problems for the exam. I posted it on Blackboard already, the practice test. In addition to the problems that I worked today, you should also expect some multiple choice, probably maybe 15 or 20, somewhere around there. About half of them drawn from the test bank, the read text. So I think the multiple choice questions there should be good practice for that. It won't be the exact same questions, but written by the same person. So one thing I wanted to talk about today is the types of errors that can happen in hypothesis testing. So let's first of all think about the decisions. I should have checked that already. It's about 6 inches off. Okay, now that we've got that going. Types of errors. First of all, just think that there are two decisions you can make in any hypothesis test. You can either reject HO. So if you get 5 standard errors away, then you're going to reject HO, or however many using our cutoff. Or you can fail to reject HO, which I will frequently just put FTR. That's fail to reject. Awesome. Okay, I'll have a little bit more editing to do. So you can either reject HO or fail to reject HO. In addition to what I'm going to tell you now, remember that if you reject HO, you can be confident up to the level of significance that you put. If you fail to reject HO, you really can't. You don't know the probabilities associated with that. So you don't say you accept HO. You just say it's plausible. It could be true. So if you reject HO, you could be correct, or you could be wrong. If you're wrong, you've made what's called a type 1 error, and the probability of a type 1 error is equal to whatever you set the level of significance to. Alpha, the level of significance. If you set, on this test, it'll be all 0.5. We'll change that next week. So before you do anything, you know that there's a 5% chance that you're wrong. That is the probability of a type 1 error. It's the probability of rejecting HO and being wrong about that. We kind of drew that graphically the other day. If HR was a greater than, and you had your 0.05 out here, you would reject HO, but sometimes HO is going to be true. You would get that some of the time, even if HO were true. So we're going to reject out here, but we would be wrong 5% of the time. Okay, so fail to reject HO. Again, you could be correct. You know, I could get a value over here, and I fail to reject HO. I say HO could be true. I could be right about that. Maybe HO is true. On the other hand, I could be wrong in that conclusion. And if you are, that's called a type 2 error. And the probability of a type 2 error is equal to the beta curve. We're not going to compute the beta curve. The most important thing you know about is it's not one value. That's why we can't associate a specific probability with it. So when we fail to reject HO, we don't know what the probability of being an error, of there being an error. Therefore, we don't say we accept HO. We just say we fail to reject HO. It could be true. As opposed to when we reject HO, we're at least confident at the level of significance that we chose. Another thing you'll see quite frequently, whether it's this text or any text in the multiple choice questions, is something about interpreting a confidence interval. So first of all, I'm just going to say, when you interpret a confidence interval, let's say you have a 95% confidence interval, you're not making a statement about that one interval. You're making a long-run statement which says, if you repeatedly sample, what proportion of intervals would include the true parameter. So I'm going to draw this out, and you'll see this picture in various places. So let's say that we have a sampling distribution based on the true, but unknown. We don't know what it is, otherwise we wouldn't be trying to predict it. But we know that there is some real mean for the population. So let's say that we know, we have our sample size, we know the standard deviation. Even if we don't, there is one. There is a true sampling distribution. But when we draw a confidence interval from that population, we might get a confidence interval that goes from here to here. In that case, you can see that the true population mean is in the interval. Doesn't have to be in the middle of it, somewhere in the interval. I could get an interval like this. I could get an interval like this. All of these intervals include the true population mean. If we have a 95% confidence interval, though, we're going to be wrong 5% of the time. We're going to construct an interval that's like this. It does not include the true population mean. So this is, in the long run, if we took many, many samples, and you would never do this, but if you did, then it's 95% of the intervals would include the true population mean, 5% wouldn't. Now when we look at this specific interval, given what we know right now, what's the chance that that one interval includes the true population mean? No, it's 100%. Look at it. It's in there. What's the chance that this one interval includes the true population mean? 0%. So when you're looking at one interval, if you had complete information, there's either a 100% chance that that one interval includes the population mean, or there's a 0%. There's a 100% chance 95% of the time. That says if we keep doing this, it's going to be in there 95% of the time, and it's not going to be in there 5% of the time. I'm not saying that's an easy concept to get at, but you have to think in the long run kind of thing. I think in a larger class, sometimes, I think I've told you this, we roll dice. And in the class as a whole, we might roll 10 dice, 250 times. Might have 25 groups of 2, each one rolling at 10. Then they would compute the mean of every one of those rolls. And then we put those means up on the board, and it looks like a bell curve. Some of those means, if we drew an interval around it, about 95% in the long run, would include the true mean, which when you're rolling dice, it ought to be about 3.5 is the average. But sometimes you make an interval that has 3.5, and sometimes, about 5% of the time, someone gets 10 dice, they roll them, and the average is 2. I'm going to try and make up a multiple choice question here, just in my head here, or at least give you some true-false kind of statements. There's a 95% chance that we form an interval. It goes from 12 to 16. There's a 95% chance that that interval includes the mean, the true population mean. True or false? 50-50 chance, guys. It's false. It's not a statement about this one interval. This interval either has a 100% chance or a 5% chance. So the true question would be something like this. If I drew many samples, 95% of the intervals will include the true population mean. So it's not about one interval, it's about a collection of many intervals. So how about this one? In a collection of many intervals, let's say an infinite number even, there is a 5% chance that the interval will not include the sample mean. False. And the reason is, I asked about the sample mean. There's a 100% chance every interval includes the sample mean because it's the sample mean plus or minus a margin of error. Okay, so there's two things you have to look for there to get these true-false. It's not a statement about one interval. It has to be a statement about a collection. And you're asking whether or not it includes, there's a 95% that you'll get an interval that includes the population mean. I'm just giving you those little kind of things where they can throw in the things. There's a 100% chance every interval includes the sample mean because every interval is computed as the sample mean plus or minus a margin of error. Same thing with every one of these. The mean's there, we have a margin of error on each side. The sample mean's in there. It's the center of every interval all the time. So be careful when you get to that question. I'm trying to get all those tricky things out here today. The p-value. Let's say that we get a problem that says, let's say we have something like this. Our hypothesized mean is 70. We get a mean of 77. And we say that the p-value is equal to 0.002. Okay, so we have a p-value there. That is a false statement. Because it's true if the population mean is 70. But if the population mean were 77, for example, then there's a 50% chance you'd be better than over 77. We don't know what the mean is, so if we're saying, here's our x bar, we can't, that 0.002 is conditional on having a population mean that's equal to 70. So the right way to say that is if the population mean is equal to 70, if the null hypothesis is true, That's the pattern of this, whether it's means or proportions or anything. If the null hypothesis is true, then there is a 0.002 chance that x bar is greater than or equal to 0.002. So whenever you're talking about interpretation of a p-value, make sure you include or look for in the multiple choice questions some conditional thing, like an if-then. If the null hypothesis is true, then there's a 0.002 chance of observing a statistic. But I'm assuming here that HR is mu greater than 70. So I just have p-value here.
That says there's a 0.002 chance that the x bar is greater than 0.002.
Oh, I'm sorry. 77. Thank you. I was all hepped up about that 0.002 thing there. Yeah, it is 77. Thank you. One other kind of, I don't know, twist to this is if HR had been mu equal to 70. Remember then your p-value is in both tails. So when we drew that, it would be like this. We have our mu equal to 70. We've observed an x bar of 77. And we have a p-value or a probability out here of 0.002. But since this is equal to, and HO would be, I'm sorry, that should be not equal to, not equal to, two-tailed test, then we have p-value on this side as well, 0.002. So the total p-value is 0.004. And this number would be 63. And that's because this distance is 7, just 77 minus 70. And so if this distance is 7, then you have to go 7 units this way as well, or 70 minus 7 to get the 63. So now when you write your p-value, it's if mu is equal to 70, then there is a 0.004 chance that x bar is either greater than 77 or I can put greater than or equal, less than or equal 63. Really doesn't make any difference if you put the equal sign there because in a continuous distribution, the area under one exact point is 0, really undefined. If you use your calculators to compute a p-value and you tell it not equal to for the hypothesis, it automatically does the doubling for you. So you don't have to double it. It is giving you the entire p-value. Also, if you see a p-value reported somewhere, it's already been doubled. If you're calculating it yourself, you'll have to remember to get the area in one and then double it to get the area in the other. But otherwise, when it gets reported, computers and calculators already know that. So let me show you something on your calculators. Let's say that we had HO mu equal to 70 and H A or HO or mu not equal to 70. So we just want to know if it's different. Either side, that's a two-tailed test. And let's say that we have a population standard deviation equal to 10. We know that. And let's say that we have a sample size of 40 and that we have an X bar equal to 72. So if you have your statistical calculators, you would hit stat, arrow over to tests, select z-test, and then just enter in into the screen there. Make sure you have stats selected for input, since I have statistics here. So for mu 0, we're going to have 70. For sigma, we're going to have, well, 10. For X bar, we're going to have 72. For N, 40. And when you get to the next part there, that's your alternative hypothesis. So select not equal to. Now, when you get to the bottom, instead of hitting calculate, hit draw. And that is the sampling distribution for this problem. And you can see that it has shaded in p-value in both sides, and that it has a p-value of 0.2059. If you calculated instead of draw to give you the same numbers, but it's kind of nice. That is the sampling distribution. If you had to draw a sampling distribution for a problem, it'll show you what it looks like. Now go back and hit stat test. This time, let's say that our HO was, or our HO will be the same, was mu greater than 70. So the only thing you need to change is the hypothesis at the bottom. Change that from not equal to greater than, and then select draw again. And now what you'll see is that you just have one tail drawn in, and that the p-value is equal to 0.103. In other words, about half of this. They didn't double it. If you went back quickly and just changed HA to mu less than 70, then you're going to see similar to the same, but only the lower tail shaded in. Okay, everything, which I know. Sorry, I should have changed that up there, but I didn't. Good. Oh, wrong thing. So it's a good thing I drew this on there. Oh, shoot, I'm still having trouble drawing that. Come on. Let me go a little more slowly with this. We have a mean of 70. Our HA was mu less than 70. But we observed 77. In other words, we're right here. So since it's less than, our p-value is in that direction. Think about this. If I want to show that the mean is less than 70, but I have 77, you're never going to fail to reject HO, because what we have here is evidence that goes the other direction than our alternative. So if you see p-values greater than 0.5, what that means is you have evidence that actually contradicts your alternative hypothesis. And sometimes that's interesting. That happens in science or business or whatever. You collect some data. You think that spending some more money on advertising will increase your sales. So you spend the money on advertising and your sales goes down. Well, maybe you shouldn't spend that much money on advertising. What could happen with advertising, of course, is that if it's a specific kind of commercial, for example, maybe you have this kind of thing, but then maybe after a while it levels off and goes down. People get sick of the darn thing. You can probably imagine. Okay. Effect size. This is becoming more and more something that people report, and they should report. What can happen with probability and statements, hypothesis testing in particular, not so much with confidence intervals, but certainly with p-values and that kind of thing, is if you take a very large sample, even trivial differences will be statistically significant. They will be unlikely by chance just because you have a large sample size. Now that seems kind of odd, but it's true. You can, from the standpoint of hypothesis testing, have a sample size that is too large. So I'll give you an example here. Suppose that we had HO mu equal to 70 and HR mu greater than 70. We still have that standard deviation of 10. Now let's say we observed a sample mean of 71 and our sample size was 4,000. So I'm going to draw a curve here. I'm drawing it like this for a reason. Our hypothesis is right here. Let's run this through your calculator. Go to z-test, put in the 70, you should have that there, the 10, change the x bar to 71 and the n to 4,000 and select greater than. And you can either do calculate or draw, that's up to you. But what you end up with is z equal to 6.324 and p is equal to that, see that e to the minus 10? That's exponent minus 10. So that means that before you get to that 127, you have 9 zeros. Which you'll admit is a very low probability. In other words, the 71 is way up here. The reason for that is that when you computed standard error, your standard error is sigma divided by the square root of n. Well, when that n gets really large, no matter what the standard deviation is, the standard error is going to get very small. The sampling distribution is going to be very narrow. So if we were stating this p-value wise, we would say if the mean is equal to 70, then there is a very small, a 0.090127 chance that x bar is greater than or equal to 71. In other words, almost no chance. We're 6 standard deviations away, which is a long way away in terms of number of standard deviations. We've rejected HO. We've concluded the mean is greater than 70. But the question is, who cares about a difference of 1 point? We're still only 1 point different. It's statistically significant, or there is a low probability of that, a very low probability, but it's because this standard deviation or standard error is 10 divided by the square root of 4,000, or just a very small number. So we're 6 of those very small numbers away. So 10 divided by square root of 4,000 is 0.158. So one standard deviation is just a 0.16 away, but let's say on scores on some test or something, that really isn't a big difference, and I wouldn't get too excited about it. So that's where effect size comes in. And basically the idea is, first we find out, we do want to know if it's likely to happen, the probability of it, but once we have that, let's ask the more practical question, or an additional practical question is that a difference that we care about? And effect size is just x bar minus mu x bar. Actually, there's a lot of formulas for it, but the one for this will be x bar minus mu x bar over just the standard deviation. So we're going to ask how many standard deviations, not how many standard errors. So that's not going to give us the probabilistic statement because we're talking about different distributions. Here we have sigma of the x's, but we're asking about x bars. But this will give us some a better sense of the size or the magnitude of the difference. So we have 71 minus 70. Now it's over 10, or 0.1. We're 1/10 of a standard deviation improvement. That's just not that much. I'm going to give you sort of a generic rule, but once you know what you're talking about or the data that you're looking at, you shouldn't use this. This is for, you know nothing about the data, just as sort of a starting place. Even the guy that came up with this, a fellow by the name of Cohen, he says, only use this early in your research. Once you know something about the data or the variable that you're looking at, use common sense. Make your own judgments there. But what he will say is he'll have 0.2, anything greater than or equal to 0.2 for the effect size. If you're greater than or equal to 0.2, you have a small effect. It's in a practical sense. If you have less than that, it's just trivial. Let's say less than 0.2 is just trivial. And then if you have actually greater than or equal to 0.2 but less than 0.5, if you have greater than or equal to 0.5 to less than 0.8, he would call that a medium effect. And if you have greater than or equal to 0.8, a large practical effect. Okay. Don't memorize those. I'll either write them on the board when you take the test or put it on some kind of sheet that I give you. It's really more the idea of it that I think is important. That is that we sort of have two things going on here. Is this likely to occur by chance? And if it's something that could happen just by pure chance, we're not going to pay attention to it. But even if it does occur by chance, we want to go one step further and say, okay, what is, in a practical sense, is that really a difference that we would care about? And maybe a 1-point difference would be something you would care about, but probably not.